Physics is the most fundamental of all the natural sciences. Its main goal is to understand how the universe behaves. It explores everything, from the smallest particles tinier than atoms to the largest structures we know, like vast galaxies. Physics seeks to find the basic rules that govern energy, matter, space, and time. It is a quest for knowledge, a journey to uncover the underlying principles that make everything in existence work the way it does. This grand endeavor helps us make sense of the cosmos and our place within its intricate tapestry. It is, in essence, the study of everything. Why should you care about physics? It is not just for scientists in white lab coats. Physics profoundly affects your daily life every single moment. The principles of physics explain why the sun shines, providing us with light and warmth. They explain why your feet stay firmly planted on the ground instead of floating away. Understanding physics helps us appreciate the world around us with a deeper sense of wonder. It allows us to see the hidden mechanisms behind the everyday phenomena we often take for granted, turning the mundane into the extraordinary. It empowers us with knowledge. Consider the technology you use every day: your smartphone, your computer, the car you drive, or the bus you take. All these devices are products of our understanding of physics. Medical imaging techniques like X-rays and MRIs save lives, and they are based on physical principles. Even something as simple as cooking involves physics, from the transfer of heat to the chemical reactions that transform ingredients. Physics is the bedrock upon which modern technology is built, constantly shaping our world and improving our quality of life in countless ways. It is the silent engine of innovation. Ultimately, physics is about curiosity. It is about asking why and how. Why is the sky blue? How do stars form? What is the nature of reality itself? These are the kinds of questions that physicists ponder. By seeking answers, we not only gain practical knowledge but also expand our intellectual horizons. Physics challenges us to think critically and solve complex problems. It fosters a way of looking at the world that is both analytical and deeply appreciative of its beauty and complexity. It is a journey of discovery that never truly ends. Take a moment to think about your morning routine. When your alarm clock rings, that sound travels as waves, a concept straight out of physics. When you flick a light switch, electrons flow through wires, creating light and heat. This is the domain of electromagnetism, a core branch of physics. Even the simple act of pouring cereal into a bowl involves gravity pulling the cereal down and fluid dynamics as the milk flows. These are not obscure scientific ideas. They are active forces shaping every tiny detail of your daily experience, often unnoticed yet always present. Physics is constantly at play. Now, consider the journey to work or school. If you drive a car, the engine is a marvel of thermodynamics, converting chemical energy from fuel into motion. The tires gripping the road rely on friction, another key physical concept. If you take a train, its movement along the tracks, its acceleration, and its braking are all governed by Newton's laws of motion. Even bicycles operate on principles of balance, gears, and energy transfer. Every mode of transportation is a testament to our understanding and application of fundamental physical laws, making our world more connected. Think about the entertainment you enjoy. When you listen to music, sound waves vibrate your eardrums. These vibrations are then converted into electrical signals your brain interprets as melodies and rhythms. Televisions and computer screens use light-emitting diodes or liquid crystals, technologies developed through research in solid-state physics and optics. The very ability to transmit these signals wirelessly across vast distances relies on our mastery of electromagnetic waves. Physics underpins the vast majority of our leisure activities, enriching our lives with sound and vision. Even your own body is a physical system. Your heart pumps blood, a fluid, through a complex network of vessels. This is fluid dynamics. Your muscles exert forces to allow you to move, which involves biomechanics. Your eyes act like lenses, focusing light onto your retinas, a principle of optics. Understanding these physical aspects of our biology helps in medicine and in designing better ways to live. Physics is not just out there in the universe. It's right here, inside you, making you work. It's deeply personal. The story of physics began long ago, with ancient civilizations observing the stars. They tracked the movements of the sun, moon, and planets. Early Greek philosophers like Aristotle tried to explain motion and the nature of matter. While many of their specific ideas were later proven incorrect, their spirit of inquiry was crucial. They laid the groundwork by asking fundamental questions about the world. They were the first to systematically try to understand the cosmos, driven by pure curiosity and the desire to make sense of their surroundings. This was the dawn of scientific thought. The scientific revolution, starting around the 16th century, brought a new way of thinking. Figures like Nicholas Copernicus proposed that the Earth orbits the Sun, challenging the long-held geocentric view. Galileo Galilei used telescopes to make groundbreaking astronomical observations. He also experimented with falling objects, challenging Aristotelian physics. His emphasis on observation and experimentation became a cornerstone of the scientific method. This period marked a dramatic shift towards empirical evidence as the basis for understanding the natural world. It was a true revolution. Then came Sir Isaac Newton in the late 17th century. Newton formulated the laws of motion and the law of universal gravitation. These laws provided a unified framework for understanding how objects move on Earth and how celestial bodies interact in space. His work, Principia Mathematica, became one of the most important scientific books ever written. Newton's physics, often called classical physics, reigned supreme for over 2 centuries. It described the macroscopic world with incredible accuracy and predictive power, leading to immense technological progress throughout the Industrial Revolution. The late 19th and early 20th centuries brought another upheaval. Scientists discovered phenomena that classical physics could not explain. This led to 2 major revolutions: relativity and quantum mechanics. Albert Einstein's theories of relativity reshaped our understanding of space, time, gravity, and energy. Simultaneously, pioneers like Max Planck, Niels Bohr, and Werner Heisenberg delved into the bizarre world of atoms and subatomic particles, creating quantum mechanics. These theories painted a new, stranger, and more wonderful picture of the universe. Physics was, and still is, an evolving adventure. Sir Isaac Newton gave us 3 fundamental laws of motion. These laws describe how things move, or why they stay still. The first law is often called the law of inertia. It states that an object at rest will stay at rest, and an object in motion will stay in motion, with the same speed and in the same direction, unless acted upon by an external force. Imagine a soccer ball sitting on the grass. It will not move until someone kicks it. Once kicked, it would keep rolling forever if not for friction and air resistance. Inertia is like nature's tendency to resist changes in motion. Newton's second law explains what happens when a force does act on an object. It tells us that the force an object experiences is related to its mass and its acceleration. In simpler terms, if you push something, it will speed up, slow down, or change direction. The more massive the object, the harder you need to push it to get the same acceleration. Think about pushing a small toy car versus pushing a real car. The real car requires much more force to get it moving. This law connects force, mass, and the resulting change in motion in a very precise way. The third law is about action and reaction. It states that for every action, there is an equal and opposite reaction. This means that if you push on a wall, the wall pushes back on you with the same force. When a rocket launches, it expels hot gas downwards, the action. This causes the rocket to be pushed upwards, the reaction. When you walk, you push backward on the ground with your feet. The ground, in turn, pushes you forward. This law highlights the interactive nature of forces. They always come in pairs, acting on different objects. These 3 laws, though simple to state, are incredibly powerful. They form the foundation of classical mechanics. They allow us to predict the motion of everything from a thrown baseball to planets orbiting a star. Engineers use these laws to design cars, airplanes, buildings, and bridges. Understanding Newton's laws gives you a fundamental insight into why things in the physical world behave the way they do. They are the basic rules for how stuff moves, and they apply almost everywhere in our everyday experience, making them essential to grasp. Section 5. The Cosmic Glue, Understanding Gravity. Beyond his laws of motion, Isaac Newton also gave us the law of universal gravitation. This law describes the attractive force between any 2 objects that have mass. Yes, any 2 objects. You, your chair, the Earth, the Moon, the Sun, everything with mass pulls on everything else with mass. The strength of this gravitational pull depends on 2 things: how massive the objects are and how far apart they are. More massive objects exert a stronger pull, and the closer they are, the stronger the pull becomes. This is the force that keeps you anchored to the Earth. Gravity is what governs the dance of the cosmos. It keeps the Moon in orbit around the Earth. It keeps the Earth and all the other planets in orbit around the Sun. The Sun itself, along with billions of other stars, orbits the center of our Milky Way galaxy, all held together by gravity. Without gravity, planets would fly off into space, stars would not form, and galaxies would not exist. It is the architect of cosmic structures, shaping the universe on its grandest scales. It is truly a universal force, acting across unimaginable distances. Think of gravity like an invisible tether. It is always pulling, never pushing. While it is the weakest of the four fundamental forces of nature at the subatomic level, its effects are dominant on astronomical scales because it is always attractive and acts over long distances. Every atom in your body is gravitationally attracted to every atom in the Earth. That combined pull is what we experience as our weight. If you were on the moon, which has less mass than Earth, you would weigh less because the moon's gravitational pull is weaker. Understanding gravity is crucial for space exploration. When we launch satellites, we need to calculate precisely how Earth's gravity will affect their orbits. When we send probes to other planets, we rely on our understanding of gravity to navigate the vast distances of space, even using the gravitational pull of planets for slingshot maneuvers to gain speed. Newton's law of gravity was a monumental achievement, providing the first mathematical description of a force that shapes our entire universe, from apples falling from trees to the majestic sweep of galaxies. Section 6. Warping reality. Einstein's revolution of spacetime. In the early 20th century, Albert Einstein completely changed our understanding of gravity, space, and time. His special theory of relativity, published in 1905, started with two simple-sounding ideas. First, the laws of physics are the same for everyone, no matter how they are moving, as long as they are not accelerating. Second, the speed of light in a vacuum is constant for everyone, regardless of their own motion or the motion of the light source. This second idea has some very strange and wonderful consequences for how we perceive the universe. One consequence is that time is not absolute. Time can pass differently for different observers depending on how fast they are moving relative to each other. This is called time dilation. Imagine a twin who travels on a super-fast spaceship close to the speed of light, while their sibling stays on Earth. When the traveling twin returns, they will have aged less than the twin who remained on Earth. Clocks moving very fast literally tick slower relative to stationary clocks. This isn't science fiction. It's a verified physical phenomenon, though only noticeable at extremely high speeds. Another consequence is that space and time are intertwined. Einstein showed that they form a single, four-dimensional continuum called spacetime. What one person measures as a distance in space, another person moving relative to them might measure differently. Similarly, what one measures as an interval of time, the other might also measure differently. However, these measurements are linked in such a way that the speed of light remains constant for both. This led to the famous equation E equals mc squared, which reveals a fundamental relationship between energy, E, and mass, m, with c being the speed of light. Einstein later developed his general theory of relativity, published in 1915. This theory describes gravity in a new way. Instead of being a force pulling objects together, Einstein proposed that gravity is a curvature or warping of space-time caused by mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. The sheet curves around the ball. If you roll a marble nearby, it will curve inwards towards the bowling ball, not because the ball is pulling it, but because the sheet itself is curved. This is how gravity works, guiding planets around stars. Section 7. The quantum leap into the subatomic realm. While Einstein was revolutionizing our understanding of the very large, another revolution was brewing in the world of the very small quantum mechanics. This branch of physics deals with the behavior of matter and energy at the atomic and subatomic levels, the realm of electrons, protons, and photons. What scientists discovered was that the rules governing this tiny world are incredibly different from the classical rules we see in our everyday lives. It's a world of probabilities, uncertainties, and bizarre dualities, challenging our common-sense intuitions about reality. One of the strangest concepts in quantum mechanics is wave-particle duality. It turns out that tiny entities like electrons and photons, particles of light, can behave like both particles and waves, depending on how you measure them. Imagine light sometimes acting like a stream of tiny bullets, particles, and other times acting like ripples spreading across a pond, waves. This dual nature is fundamental to the quantum world. It is not that they are one or the other, they are somehow both simultaneously, until we try to pin them down with an experiment. Another key idea is the Heisenberg uncertainty principle. This principle states that there are fundamental limits to how precisely we can know certain pairs of properties of a particle at the same time. For example, the more accurately you know the position of an electron, the less accurately you can know its momentum, how fast it is moving and in what direction, and vice versa. This isn't due to a limitation of our measuring instruments, it is an inherent feature of nature itself at the quantum scale. The universe has a built-in fuzziness when you look closely enough. Despite its weirdness, quantum mechanics is one of the most successful scientific theories ever developed. It forms the basis for our understanding of chemistry, how atoms bond to form molecules. It is essential for many modern technologies: lasers, transistors, the building blocks of computers and smartphones, medical imaging like MRI, and nuclear energy all rely on quantum principles. Without quantum mechanics, much of the technology that defines our modern world simply would not exist. It is a testament to how exploring the fundamental nature of reality can lead to profound practical applications. Section 8. Today's puzzles: unraveling cosmic mysteries. Physics is far from a completed subject. While we have learned an enormous amount about the universe, there are still many profound mysteries that physicists are actively trying to solve. One of the biggest puzzles is the nature of dark matter. Observations of galaxies and galaxy clusters show that they are spinning much faster than they should be if we only account for the visible matter: stars, gas, and dust. This suggests there is some invisible dark matter providing extra gravitational pull. We can see its effects, but we don't yet know what it is made of. Then there is dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down, as might be expected due to gravity. Instead, it is accelerating. To explain this, physicists have proposed the existence of a mysterious force or energy, dubbed dark energy, that permeates all of space and pushes everything apart. Together, dark matter and dark energy are thought to make up about 95% of the total mass energy content of the universe. The ordinary matter that makes up stars, planets, and us is only a tiny fraction. Another major goal in fundamental physics is to find a theory of everything. Currently, we have two incredibly successful theories: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the other forces and the behavior of matter at the smallest scales. However, these two theories are not fully compatible. They use different mathematical languages and give nonsensical answers when applied to situations where both gravity and quantum effects are strong, such as inside black holes or at the very beginning of the universe, the Big Bang. Physicists are exploring various approaches to unify these theories, such as string theory and loop quantum gravity. These are highly complex mathematical frameworks that propose new ideas about the fundamental nature of space, time, and matter. The search for this unified theory is one of the ultimate challenges in physics. Solving these cosmic puzzles requires new ideas, new experiments, and perhaps even new ways of thinking about reality itself. The quest for understanding continues, pushing the boundaries of our knowledge ever further into the unknown depths of the cosmos. Section 9. Tomorrow's World: The Future Forged by Physics. The ongoing quest to understand the universe through physics will undoubtedly lead to incredible future innovations. Consider energy production. Physicists are working on harnessing nuclear fusion, the same process that powers the sun. If successful, fusion reactors could provide a clean, virtually limitless source of energy, transforming our planet and addressing climate change. This involves taming plasma hotter than the sun's core, a monumental challenge requiring deep understanding of electromagnetism and plasma physics. The potential benefits for humanity are truly immense. Quantum computing is another exciting frontier. Unlike classical computers that store information as bits, zeros or ones, quantum computers use qubits. Qubits can be 0, 1, or a superposition of both, thanks to quantum mechanics. This allows quantum computers to perform certain types of calculations exponentially faster than any classical computer. They could revolutionize fields like medicine, designing new drugs, materials science, discovering new materials with unique properties, and cryptography, creating unbreakable codes or breaking existing ones. The dawn of the quantum computing age is approaching. Advances in material science, driven by our understanding of condensed matter physics, will continue to bring us novel materials. Imagine ultra-lightweight and super-strong materials for building more efficient vehicles and spacecraft, or superconductors that can transmit electricity with no energy loss, revolutionizing power grids. Perhaps even smart materials that can adapt their properties on demand. These new substances, designed at the atomic level, will enable technologies we can currently only dream of, from better batteries to more efficient solar cells. Ultimately, physics is about expanding our horizons, both technologically and existentially. It helps us understand our place in the vast cosmos and our connection to its fundamental laws. Future discoveries in areas like cosmology, particle physics, and astrophysics may answer age-old questions about the origin of the universe, the nature of time, or the possibility of life elsewhere. Physics will continue to shape human civilization, driving progress, solving critical global challenges, and deepening our awe and appreciation for the intricate, beautiful, and often mysterious universe we inhabit. The journey of discovery is far from over.